This is problem 38 from electric potential. In the previous problem, which was problem 36, we saw that the net potential was equal to the potential from charge 1 plus the potential from charge 2. And in general, you could say the net potential is equal to the sum of the potential from each individual electron and proton. This is on page 7. And when we had a similar expression for the electric field, we saw that this implied, when you have a continuous charge distribution, that the electric field could be found by integrating, and so we have something similar for the electric potential. I'm not going to say anything more about it. We're just going to say that because it worked for the electric field, it works for the potential also, so our new expression for a continuous charge distribution becomes K times dq over R, and we integrate that to get the potential. They give us 7 steps for successfully solving the electric potential from a continuous charge distribution on page 7, but fortunately they also give us those steps on page 38, so we will just follow along, and it shouldn't be that bad because it's very similar to what we did for the electric field. So first we carefully identify and label S, the location of the differential element. The differential element has to be where there is charge, so that's going to be somewhere on my rod, and the distance to that point is S. The differential element itself you can call either ds or dq. I don't have a lot of room on my diagram, so I'm not going to label it up there. So this is ds, it's going from the origin to my differential element. And just like in the electric field, you don't have to go from the origin. You can go from the left side of the rod to the right side of the rod. You can even get more creative than that, but the origin is a good place. Carefully identify and label X, the location of the point of interest. So we are looking for the electric potential at all points on the x-axis to the right of the rod, so we pick an arbitrary point on the x-axis, and the distance to that point is x. Write an expression for dq, the charge on the differential element. We do this the same way that we did for the electric field. dq is equal to, they give us the charge and they give us the length, so that is q over L times ds. Because the charge is uniformly distributed, it is true, just like it was in the electric field section, that the linear charge density is equal to the charge on the whole rod divided by the length of the whole rod, or the charge on a small differential element divided by the length of that small differential element. And in this case, because they gave us Q and L, we're going to use this to write in our expression for dq. Then we have to write an expression for R, the distance between the differential element and the point of interest. That distance is from here to here, and that is x minus s. That distance is positive, as it should be. And so we can just say R is equal to x minus s. Then we are going to write an integral expression for the electric potential, choose the limits of integration, and calculate the integral. So this is our equation for the electric potential. K is just equal to K. dq is equal to Q divided by L times ds. And in the denominator, I have R, which is x minus s. I'm integrating over everywhere there is charge, which is from one end of the rod to the other end of the rod when I am here, because I chose s to be equal to 0 at the origin. This is equal to negative L over 2, so I'm going from one end of the rod to the other end of the rod, so that's from negative L over 2 to L over 2. The K, the Q, and the L are all constant, so I can pull out a KQ divided by L. I'm integrating from negative L over 2 to L over 2, and I have ds over x minus s. I'm going to do a u substitution here and say that u is equal to x minus s, which means du is equal to negative ds, and we did something similar to this in the electric field section. So my integral becomes the integral of ds would be negative du, and my denominator would be u. And so I have the negative sign here, and then the integral of 1 over u with respect to u would be the natural log of u. And then I can go ahead and put in my limits of integration after I go back here and say u is equal to x minus s, so this is the natural log, oh, and I got to remember the negative sign, of x minus s as I go from negative L over 2 to L over 2. So I can go ahead and plug that in. Remember that subtracting natural logs is the same as dividing, and so we can write that as negative kq over L times the natural log of x minus s, where s is equal to L over 2 for the upper limit, so that's x minus L over 2, divided by, it's supposed to be, you're supposed to subtract the natural log of x minus negative L over 2, but that would be the same thing as saying divided by x plus L over 2. And then I can take this negative sign that I have here and rewrite my expression as kq over L times the natural log of x plus L over 2 over x minus L over 2. And since x is to the right of the rod, x is always going to be greater than L over 2, so I don't really need the absolute value signs here because that is always going to be positive. And remember, it's a scalar quantity, so there's no unit vectors to worry about. So this is my answer. And I have some questions to answer. At x is equal to L over 2, what should the potential be equal to? Well, remember that before we did the integral, we said you could find the potential by summing up the potential that you have for each individual charge. So right at the end of the rod here, you would have a positive charge. And what happens to the potential when you're right on top of a positive charge? It goes to infinity. So as you get close to the end of the rod, the potential should be going to positive infinity because you have positive charge right on the end of the rod. So V should equal infinity. Does our expression agree? If x is equal to L over 2, then in the denominator here we would have 0, and so that would agree. If x is much, much larger than L, if you're so far away from the rod that you can't even tell it's a rod anymore, it just looks like a point charge, then the potential would be K times the net charge divided by the distance from the charge to the point of interest. And if you're really, really far away, it just looks like all the charge is here at the origin and not distributed over a rod. So that would just be K times Q divided by X. Does our function agree with this observation? I don't know about that. But we can say, as we go really, really far away, our function goes to 0. As x goes to infinity. So I don't exactly know if that's what they wanted us to compare, but we could say this: as x goes to infinity, this potential also goes to 0. So if x is going to infinity, yes, they agree, and we'll leave it at that.